So far we've used integrals to compute areas and volumes, and it turns out that we can use them to compute lengths of curves also. So the idea is that we want to know what is the length of the curve. Let's say we have a curve here. And the idea is that we're going to draw line segments to approximate the curve. And each line segment is going to have horizontal length delta x and height delta y. Then each one of those line segments makes a right triangle. And if we know the height of the rectangle, the triangle is delta y and the width is delta x, then that means on the hypotenuse what's here must have length delta x squared plus delta y squared. So the sum is something like sum of square root of delta x squared plus delta y squared. And if we factor a delta x out of this, then it looks like 1 plus delta y squared over delta x squared. Now in the limit as the length of the segments goes to 0, or the number of segments goes to infinity, we have an integral. This delta x is going to turn into a dx, and what's inside the square root becomes 1 plus dy dx squared. So 1 plus the derivative of the function squared. Now there's only one problem. As I've said many times, the human race is not that good at integrating. And it turns out that these integrals are usually things we can't do. So the problem is we usually can't integrate this. But as an example, let's start with one that we can do. Usually can't integrate this. Let's start off with an example we can do. Let me put this formula on top. So it's the integral of 1 plus derivative squared dx. Let's find the length of y equals x to the 3/2 from x equals 1 to x equals 9. This is, let's see, f of x is x to the 3/2. F prime of x then is 3/2 x to the 1/2. and f prime of x squared is 9/4 x. Alright, so what we have is the integral as x goes from 1 to 9 of the square root of 1 plus the square derivative 9x over 4 dx. Alright, what's on the inside of the square root has a derivative of 9/4. So I kind of wish I had 9/4 dx here. So I will put 9/4 dx here and multiply by 4/9 on the outside so that I'm not changing the problem. Then this is 1 plus 9x over 4 to the 1/2 power. Let me write it that way. So foo to the 1/2 d foo has integral foo to the 3/2, 1 plus 9x over 4 to the 3/2 divided by 3/2. And then we want to integrate this from 1 to 9. Alright, so it looks like our constant on the outside is 8 over 27. And then we plug in 9, plug in 1, and subtract. So if we plug in 9, we've got 81/4 plus 1. So I guess that's 85/4. To the 3/2. Minus, plug in 1. We've got 1 plus 9/4. So I guess that's 4/4 plus 9/4, 13/4. To the 3/2. And I guess we can pull out the 4 if we want to simplify a little bit. Square root of 4 is 2. Raise 2 to the 3rd power and we get 8. So we can pull out an 8, pull out an 8. So I guess we don't need this 8 anymore. So this is 1/27, 85 to the 3/2 minus 13 to the 3/2. So that's the length of x equals 3/2 from 1 to 9. Now 3/2 is a very special function because it gives us, when we take its derivative and square the derivative and put that inside of a square root, it gives us 1 plus 9x over 4, which is something we can integrate. But just to show you that's special, let's change the problem a little bit, and let's say we're looking at square root of x instead of x to the 3/2, so x to the 1/2. Let's find the length of square root of x, x to the 1/2, from x equals 1 to x equals 9. So f of x equals x to the 1/2. F prime of x equals 1/2 x to the negative 1/2, which is 1 over 2 square root of x. And then f of x squared is, I guess, 1 over 4x. So the length is integral from 1 to 9 of square root of 1 plus derivative squared 1 over 4x dx. I guess I could write this as 4x plus 1 over 4x in case that makes it easier. And then I guess I could take the 4 out of the square root and make it a 2. So we have 4x plus 1 over 2 in the square root. Oops. Sorry, that's over x. We took the 4 out, it became a 2, but we had to leave the x in there. 4x plus 1 over x. Now look at all of these different expressions for the same integral, and it doesn't look like something I know how to integrate. Maybe I haven't looked at it hard enough, but I just don't see how to do it. Well, if I can't do an integral, I can approximate the integral. So let's approximate this using, say, the trapezoid rule. So let's approximate using the trapezoid rule with two trapezoids. So we've got an interval from 1 to 9, so we could break that up into 2 pieces. I guess we could break it up into 4 pieces or 8 pieces if we wanted to, but let's just say 2 trapezoids. Over the intervals are going to be 1 to 5 and 5 to 9. So that'll get us the integral from 1 to 9, an approximation for the integral. So here's the integral we're approximating. So the integral is approximately, if we use a trapezoid with the trapezoid rule with 2 trapezoids, we've got base times average height, f of 1 plus f of 5 over 2, plus base is 4 again, times average height, f of 5 plus f of 9 over 2, which I guess is 2f of 1 plus 2f of 5 plus 2f of 5, so plus 4f of 5 plus 2f of 9. Alright, now if we plug in these values to the function here that we want to integrate, f of 1 is, let's use this expression, 5/4. 2 times square root of 5/4 plus 4 times square root of, if we plug in 5, we've got 21 over 5. So, oh, actually this has a half in it. I forgot the 1/2. Plus 4 halves, 21 over 20. Oh, 21 over 5. Plus 2 halves, we'll plug in 9, 37 over 9. And I guess we can simplify that a little bit. We can take out a square root of 4, we can simplify 2 over 2. So that's 1 square root of 5 over 2 plus 2, we can't simplify this anymore, square root of 21 over 5 plus 1, we can take out a square root of 9, which becomes 3 on the outside, square root of 37. So that's our trapezoid rule approximation of the arc length. Or we could use Simpson's rule. Let's say with 2 parabolas over the intervals from 1 to 5 and 5 to 9. Alright, now the integral I erased, but it was alright, so the integral was 1/2 integral from 1 to 9 of square root of 4x over 4x plus 1 over x. So we've got base, which is going to be 4 times 1/6 f of 1 plus 4/6. Halfway between 1 and 5 is 3. F of 3 plus 1/6 f of 5. So it's our first parabolic approximation. Plus 4 times 1/6 f of 5 plus 4/6. Halfway between 5 and 9 is 7. F of 7 plus 1/6 f of 9. So the integral is approximately 4/6 is 2/3 f of 1 plus 16/6 is 8/3 plus 8/3 f of 3. And then we've got 4/6 f of 5 plus 4/6 f of 5, which I guess is 4/3 f of 5. Plus 16/6, which is 8/3, plus 8/3 f of 7, plus 4/6, which is 2/3 f of 9. And that is, now when we plug in when we plug in 1, we've got 1/2 square root of 5/4. So 2/3, 1/2 square root of 5/4 plus 8/3, 1/2, plug in 3, and we've got 13/3 in the square root. And then plus, we're on the 4/3 part, 4/3, 1/2, f of 5 is square root of 21/5. And then plus 8/3 times 1/2, f of 7, square root of 29/7. Plus 2/3 times 1/2 f of 9. 4 times 9, 36, 37/9. And I guess there's a fair amount of simplification we can do here. 2's cancel, we have 1/3, and then the 4 can come out. So I guess it's 1/6 square root of 5. And then 8/2 is 4. So 4/3 square root of 13/3. And then here 4/2 is 2, 2/3. Square root of 21/5. Plus 8/2 is 4, 4/3 square root of 29/7. And finally 2's cancel, 1/3, and we bring another 3 out, so 1/9 square root of 37. And I think that's all the simplification we can do. The end.